Given the acceleration function of a particle, we can find its position, particularly if we have initial conditions, which we do here. We're going to find the velocity and position of a particle whose acceleration is sine of ti plus 2 cosine of tj plus 6tk. Initial velocity v at 0 is negative k. Initial position r at 0 is j minus 4k. Remember that velocity is the integral of acceleration. So in our case, our velocity at t is going to be the integral of the sine of ti plus 2 times the cosine of tj plus 6tk dt. A couple of things. This is an indefinite integral, and so we're going to pick up a constant of integration, but that's where the initial condition is going to come in. Another thing is, even though this is a vector function, we still need the differential dt. And then the third thing, I ask that you keep this all together as an integral. Some folks want to use 3 integrals, and that's okay. Each one would have to have the differential dt. We'd still keep the components I, j, and k. The point here is we have a vector to begin with. We need to have a vector throughout. Don't split it up into integrating the sine of t over in some place and then 2 times the cosine of t somewhere else and then eventually 6 times t. Keep it as the structure of a vector, please. Here, by anti-differentiating, we find that v of t is equal to negative cosine of ti plus 2 times the sine of tj plus 3t squared k plus c, a vector constant of integration, or constant vector of integration. A little note here, when I anti-differentiated the sine of t, I wasn't sure really right away if it should be cosine of t or negative cosine of t. Generally speaking, what I'll do is I'll integrate it in my head and then differentiate real quick and see if I should change the plus and minus, right? I know the derivative of the cosine is the negative sign, so the antiderivative of the sine should have a negative in front of the cosine. Well, moving on here, I've noticed that folks often have a challenging time dealing with an initial condition if they're working with a vector function. So let's see how this goes. V of 0 is what happens when we put 0 in place of t in the velocity function. So here it would be negative cosine of 0i plus 2 times the sine of 0j plus 3 times 0k plus c. That's not where the problem comes into play. It's v of 0 is supposed to be negative k. What do I do with the negative k? Well, folks, v of 0, all of that we just wrote down, is equal to negative k. What we're after is, I want to know what to put in place of the vector function, the constant vector c. So let's simplify our components and see what we have. Cosine of 0 is 1, so I have negative I. Sine of 0 is 0. And then 3 times 0 for the k component is 0. So what I have is negative I plus c, the vector c, is equal to negative k. Therefore, I know that c is equal to I minus k. Now I'm going to take that vector c, which is I minus k, put it in place of c that first time that we picked up the constant of integration. So v of t is equal to negative cosine of ti plus 2 times the sine of tj plus 3t squared times k plus c, which is I minus k. Gathering together my like vector components, I get v of t is equal to 1 minus the cosine of t, that quantity is the component of I, plus 2 times the sine of tj, because there was no j component in the constant vector c, so the j component should not change, plus the quantity of 3t squared minus 1 k. So that constant vector c showed up a little bit in the I component and a little bit in the k component because, after all, c is I minus k. That gives our velocity function. I'd like for you now to use the fact that r of 0 is equal to j minus 4k and the velocity function that we just came up with, and find the position function here. Go ahead and pause the video and come back when you're done. Well, here's what I came up with. Recalling that r is the antiderivative of v, r of t is going to be the integral of 1 minus the cosine of ti plus 2 times the sine of tj plus 3t squared minus 1k dt. So r of t is equal to 1 minus the sine of t times I minus 2 times the cosine of t times j plus t cubed minus tk plus our constant vector of integration, which I'm going to call d because we already used c in the previous step. I don't want to reuse a variable there. It's not just that I don't want to, it's actually wrong to reuse the variable there. Anyway, our initial condition was that r of 0 was equal to j minus 4k. So we have r of 0 is equal to 0i, putting 0 in place of t and in t minus sine of t, minus 2j because the cosine of 0 is 1 for the j component there, plus 0k, plus d is equal to j minus 4k. Solving for d, by adding 2j to both sides, we get d is equal to 3j minus 4k. So combining those components with the r of t that we already came up with, we have that r of t is equal to the quantity of t minus sine of ti plus 3 minus 2 cosine of tj, where that 3 is coming from d, plus t cubed minus t minus 4k, where again that minus 4 is coming from d. And that is our position function.